Welcome to new session on a virtual memory. What we have till now, we have learnt about uh, uh, memory hierarchy. We had seen that what all the various types of memories are and how these are organized inside a computing system. Then we had seen how the memory is partitioned. So we had talked about a static and dynamic partition, as well as we had talked about a fixed size partition and variable size partition. While discussing the fixed size and a variable size partition, we had encountered issues of internal and external fragmentation, and we'd seen that what the internal and external fragmentation is, and eventually what we had done, we had talked about certain techniques which are used for managing the memory. So predominantly we have discussed about demand paging, load on demand, and then we had also talked about a demand segmentation. Now in today's lecture, what we are going to describe about is notion of a virtual memory, and the notion of a virtual memory arises primarily for one reason, that if we look at any computing machine, or if we take an example of Intel Pentium processor, so we find that a Intel Pentium processor has a 32 address lines, and this 32 address line would essentially mean that the total number of total amount of memory which can be interfaced with this particular processor would be 2 to the power 32, and that is a 4 gigabyte. And we also know that most of the system, the memory is byte organized. So the maximum physical memory which can be associated with a Pentium machine perhaps is a 4 gigabyte. Of course, current day newer processors, they support a much larger amount of memory, but any given processor would support a maximum amount of there would be some upper limit maximum amount of physical memory that can be connected. We have also noticed the fact that more often than not, the machines, they do not have maximum amount of physical memory. For an example, if maximum amount of physical memory supported is a 4 GB, we might have a machine which has only 2 GB of RAM. So, but then user, we notice that the user would be able to execute a program which could be as big as a 4 GB. So how this becomes possible? So this becomes possible predominantly because of the fact that because of the notion of the virtual memory. So we will try to discuss it in this particular lecture. So if we talk about a virtual memory, so virtual memory is a is a kind of a thing which separates the user logical memory from a physical memory. So it is a separation of a user's logical memory from a physical memory. Let us understand it in this way, that any processor has an instruction pointer. So for an example, if you talk about a Pentium processor has a register which is known as a EIP, extended instruction pointer, and this register is a 32 bit, and this register is used for accessing the instructions from the memory. So the value, the register value can vary. Register value is used, the IP register is used for addressing the instructions. And we know, since if it is a 32 bit, then the total a program can generate an address which will vary from a 0 to 2 to the power 32, that is a 4 gig. And each program each executing program can generate that much address. So, if we are talking about a computing machine which has only 2 GB of a RAM, but there could be hundreds of processes which are active in the memory, and potentially each of the processes could actually access 4 GB address space. So, this 4 GB address space which we are talking about is the address space which a program tries to access through the instruction pointer register by changing the value of an instruction pointer register. So, this we call as a logical address, and these logical addresses are required to be mapped onto the physical memory, or a physical memory is to be mapped to the logical memory. So there is a mapping which is required, and a virtual memory we say is a separation of a user logical memory from a physical memory. We know that loading the entire program in memory is wasteful. So, this gave rise to a concept of a load on demand, and therefore, at any given point of a time, only part of the program that is needed is loaded into the memory. Rest of the part of a program resides on a hard disk, and therefore the logical address space can be much larger than the physical address space. Like actually a program could actually be allocated at a given point of a time probably 100 KB, whereas the entire code for that application might actually execute a program which will be a 4 GB program. So, with very limited amount of a memory, one would be able to execute the much bigger program, and this becomes possible because of a fact that because of a feature of load on demand, and we would also see that this kind of a thing allows the address space to be shared by several processes, and it also allows for a more efficient process creation. We know that a virtual memory can be implemented either via demand paging, or it can be implemented by demand segmentation. So, we'll now describe a bit about demand paging, and so for a demand paging, what happened that the concept is that a page is brought into the memory only when it is needed. So for that reason, if suppose we have a program which is a say 100 MB program, now if we need to bring an entire 100 MB of a program, then we know that it is going to require a large amount of I/O, because each while one is trying to access the information from a hard disk, and if we say that the basic unit which can be accessed from the hard disk is say a sector, then and a sector being a 512 byte, then we know that for a 1 KB we require two IOs. We require to perform for reading a 1 KB data we require two number of disk operations. So, for a 100 MB we can find out that 100 into 1000 into 2, that is the number of IO which is going to be required. But if we say that load on demand is going to be there, then probably we can only load probably a 10 KB, or probably we can load a 20 KB or 100 KB into the memory and save all the IOs. And because of a load on demand feature, there is a less memory requirement for each process. Since lesser amount of IO is going to be carried out, so the response would be faster, and since each process is going to require a smaller amount of a memory, so more number of processes or more number of a user can be accommodated into the system. So the load on a demand functions in this way, that whenever a page is needed, processor would generate a reference to a required page. Now, when the processor generates a reference to the required page, so there can be a two situation which can actually occur. One, the reference is a invalid, meaning to say that a processor has generated an address which is an invalid address, or it is trying to access information which does not belong to this particular process. So in that case, what happened that for invalid references the process can be aborted, and the another case can be that what happened that the reference is a valid reference and valid reference, but it is not in memory. So if it is not in a memory, then what happened that we need to bring that particular information into the memory. So we need to assign a frame, and we need to read a page from the backup store and bring that particular information into the memory. So this is how the demand paging usually works. So let us look at let us look at a thing that how these things are organized in the system. So here what we do, we try to give you a very simple explanation or a very simple organization here. So we say that each page with the page table usually will have a number of entries. Each entry would correspond to a one page. So what happens with each of the pages, what we do, we associate a valid and invalid bit. So which is a single bit flag, So what happened that here we in this diagram we can see that we have a frame number and then we have a valid and invalid bit. So for a given page index, we need to find out what is the frame number, and this valid and invalid bit tells me the information whether this particular required frame is present in memory or not present in memory. So if the value of valid invalid bit is a 1, it means that the frame is present in memory. If the value of a valid and invalid bit is 0, it means that the frame is not present in the memory. So this is how so we can maintain a table with page table like this with a valid and invalid bit. Now initially when every frame is empty, so what is done that these valid and invalid bits are initialized to 0. So all entries in the page table would have a valid invalid bit equals to 0. So here we have shown a snapshot where we say that it is indicated that there are a few number of frames which are loaded and there are few numbers of a frame which are yet not brought into the memory. So this is what is indication here, and so what happened that whenever from the logical address, whenever the address translation is taking place, so from the logical address we find out a page number, and from a page number when frame is going to be obtained. So when let's say that somehow we index into an entry where the valid and invalid bit is 0, this essentially means that this frame which we trying to access has yet not been brought from the secondary storage into the main memory, and as a consequence the corresponding data or instruction is not available for the purpose of processing or for the purpose of executing. This situation we call as a page fault. So this is what we are saying here. We say that during address translation, if valid invalid bit in a page table entry is 0, then a page fault is going to occur. Now so this is how we've seen that what a page fault is. But if we start, let us assume that we have created a page table, a process is just beginning. So in the beginning none of the pages are brought into the memory. So, whenever there is a reference to a page, the first reference is always going to cause a page fault. It will generate a trap to the OS, it will generate a page fault. A first reference to any page is always going to cause a page fault, primarily for the reason that there is a load on demand, and until unless you reference is you need it, the page is not brought in the beginning. So, first reference is always going to result into a page fault. So, now what, whenever the page fault occurs, what OS does, OS looks for a looks into the table and tries to find out whether whether the reference is a valid reference or a invalid. If it is invalid, that in that case it will abort, and in case it is a valid and it is just that the frame has not been page has not been brought into the memory, then it is the case that it is not in memory. So, when the frame is not present into the memory, then in that case what operating system does, operating system makes a request, it tries to get an empty frame, and after having obtained the empty frame, what it does, it swaps page into the frame. That is, from a secondary storage it brings in the page, loads the page into the frame, and after loading the page into the frame, it goes and it changes the reference bit or valid or invalid bit in the page table. So, in the beginning, as we had earlier said, that in the beginning all the frames will have a valid invalid bit equals to 0. Now, once the page has been loaded into the memory, the validation bit is going to be changed to 1. After having done this, then once again it is required that the instruction which caused the page fault should restart. So, we re-execute the instruction, the same instruction which had caused the page fault. So, this particular thing we will try to explain with the help of a diagram. So, in this case, let us say that we have an instruction which is a load instruction. So, that essentially tries to access some memory location from where it tries to load the data. So, the first thing is that a reference is generated to the memory location into the page table. So, from the logical address you get an entry into the page table, and from page table you check whether the value of I is 1 or 0. So, if we take a case where page fault has occurred, then the value of this I would be 0. So, when the value of reference bit is 0, then what it does, it generates a trap to the operating system. So, operating system now, once the trap is generated to the operating system, that essentially means that a page fault has occurred. So, when the page fault has occurred, now what operating system needs to do is prepare for handling the page fault. So, as part of this exercise, what operating system does? Operating system first makes available a frame where the page which is stored on a secondary storage is brought in. So, that is the first step, that operating system would make a request for a free frame. It will find out a free frame, and what it does, it generates the backing store address, and from there it initiates the swapping operations from a storage to the frames. So, in a step number 4, you can see that the information is brought into the missing information is brought into the frame. Once the missing information is brought into the frame, then what operating system does, it goes and updates this page table. So, what it will do, it will appropriately write the frame number here, and this particular bit it will change it to a 1, and after having done this, then restart, load M instruction will once again get executed, and when it gets executed, next time what happens, since the frame has been brought into the memory, page fault would not occur and the instruction would execute successfully. So this is how the page fault handling is carried out. So in this case, while talking about a page fault handling, our assumption was that probably we said that we would look for a free frame, and we assumed that a free frame is available. Now there is a possibility that you need to bring in a new page, but there is a no free frame. So because of this fact that there is a no free frame, then how do I bring in? So how do I bring in a new frame? So for this there are certain frame replacement algorithms, we call it as a page replacement algorithm. So what happens that we try to reuse certain frames which have been used earlier and they are still not free. So this gives rise to what we call as a page replacement strategy, and page replacement strategy is a strategy which finds some page in memory, and the approach is that it tries to find out some page in a memory which is not in use, so that it can be utilized for bringing in a new information. So the question here is that we would need to have a strategy of selecting an existing frame for the purpose of swapping in the information. So we would have this gives rise to several algorithms. We will see that what those algorithms are. And whenever we talk about an algorithm, we will always talk about performance of algorithms. And in case of a page replacement algorithm, our objective would be that the page replacement should result into a minimum number of a page fault. Otherwise, it is possible that we have a frame which is in use, and when we want to bring in a new page, we bring in and replace the existing frame, and it is possible that the very next reference could be to a frame which has been just swapped out. So it is really very important that we should have an algorithm which will result into a minimum number of a page fault. And we can very clearly see that since we are going to replace, so it is possible that same page may be brought into the memory several times. Several times it could get swapped out and swapped in. So we will actually any strategy which or a algorithm which we propose would aim at reducing the page fault and reducing such activity. Because if a page is going to be swapped in, swapped out large number of times, this essentially means that I/O overhead is increasing. So one would make an attempt to reduce the I/O overhead. When we talk about algorithms for a page replacement, immediately what we need to do is we would need to measure the performance of a given algorithm. So we said that one of the performance measure was in terms of what we said as a number of a page fault, but here what we are trying to look at, that whenever the page fault is going to occur. So let us see that what is the process that when the page fault occurs. So there is a program, and since it is a load on a demand, so only a part of a program has been brought and a part of a data has been brought. Now whenever the program tries to reference to a memory, there is a possibility that this frame may not exist into the memory. So as a consequence, a page fault occurs, and as part of a page fault handling, one would go and read the page table, and after reading the page table, it will try to bring in the information from a secondary storage into a main memory, and then update the page table. So these are the things which are going to cause a extra, they are going to add up, they are going to act as a page fault overhead, and they will add up to the access time. So another performance measure would be in terms of how much time it takes to service a request in a case of a page fault. So we define something known as a page fault rate, and we say that the value of a page fault rate is going to be 0% to 100%. So that would mean that its value would change from 0 to 1. Page fault rate P would change from 0 to 1. If value of P is 0, it is indicative that there are page fault rate is 0, no page fault occurs, and if value is equal to 1, then that essentially means that every reference is resulting into a page fault. So we try to give a generic formula which will help me to find out a effective access time, and we say that there is a P amount of page fault, P or at any given point of a time or in a given system. We say that the page fault, the P is the percentage of a page fault which occurs. So in that case, we can very clearly see that our formula will become 1 minus P. That is 1 minus P is an indicative that amount of references which does not result into a page fault. So when the amount of references that those references which do not result into the page fault, then the access time is going to be equal to the access time of a memory access time. There are no other additional overheads associated. So 1 minus P, so formula becomes 1 minus P multiplied by memory access time, and then the second part is a P P multiplied by a page fault overhead. That is you have a percentage of a P percentage page fault multiplied by the page fault overhead. So and page fault overhead would constitute things like swap page out, swap page in, and restart overhead. So all these things put together, they form the page fault overhead. So if we just try to take an example, so we say that memory access time is 1 microsecond, and we say that 50% of the time the page that is being replaced has been modified and therefore needs to be swapped out. So and we say that if swap page time is 10 millisecond, that is equal to 10 microsecond, then effective access time can be computed in this way, and we can very clearly see that the value which is going to be there is it will turn out to be 1 plus 10,000 P's. So smaller the value of a P, we find that we would have a better efficiency. Better the efficiency is going to be, and so whenever we are talking about a page replacement, so let us also understand that we have pages, they are of a two distinct type. The one page which is brought into the memory and has never been modified. So we might have this predominantly occurs mostly occurs with code. That once the program which is to be executed is brought into the memory, the program never changes, the content of a program never changes. So you have frames which contain the program, and their value, the value is not going to change, whereas the data which has been brought into the memory, there is every likelihood that this data would have been operated upon, and the data would have changed. So now when we talking about a replacement, so there can be a scenario where we have a page which is a absolutely clean page, meaning to say it is not modified, and we have another category of a page which has been modified. So that if we logically think, we know that the page which has not been modified, so a one old copy, when I am swiping it out, I need not go and write back onto the hard disk, because there is a no change. Whatever the copy which is residing on a hard disk and the copy which is residing in a main memory, they are one and same, then there is a no change in that. Whereas a page which has been modified, we find that these two copies, they differ, meaning to say the in memory page differs from what is stored on the hard disk. So if this frame is required to be replaced, then in that case it becomes a mandatory that this frame is written back. So to reduce, so how do we handle the situation? So one of the simplest way would be that every time you replace a page, what you do, you go and write it back, irrespective of the fact whether it has been modified or not. But then we know that in that case we are unnecessarily writing the frames which are not modified onto the memory, and we are unnecessarily doing a IO operation, and that will actually cause a degradation of a performance of the system. So another better approach would be that what we do, we only write the frames which are modified. And for that reason, then essentially it means that we would need to have a mechanism of knowing that some page has been modified or not modified. And that's the reason that what happened, that most of the architecture, what they do, they provide one extra bit which they call as a dirty bit, and the dirty bit, if it is set to 0, it is indicative of that the page has been the existing page in the memory has not been modified, and if the dirty bit is 1, then it is indicative of that it has been modified. So the operating system, whenever it is taking a decision, it selects a victim, it checks if the dirty bit is 0, then it doesn't write it back, otherwise it makes effort to write it. So this is how the how the optimization is carried out. Now, so having seen that when we are doing a replacement, how do we handle the writing back operation? Now, next thing is that the question is that which page to replace. That is the biggest question which needs to be resolved. So as the common sense would say that any page which is least likely to be referenced in the future should be one which should be chosen as a victim. So this is a kind of a policy which one would need to set for the replacement algorithm. So for there are various numbers of algorithm, as just now we said that we need to have a probably page which is least likely to be used in the future is the one which is the most suitable one. So this gives rise to some kind of algorithm. This gives rise to a specific algorithm. So if that is the case, that we say that we need to select a page which is least likely to be used in the future, that would mean that we would need to have some kind of a mechanism to predict the future references. If we can precisely predict the future references, then we can actually design this kind of a policy, but we know that this is going to be a little tough. Whenever we are going to carry out a replacement, there are scenarios where what we need to do is we need to resort to what we call as a frame locking. The basic idea here is that we say that if the frame is locked, then this frame frame need not be replaced. So when do we require such kind of a frame locking? So example would be that the IO buffers, where when let's say that a process is when the some IO operation is taking place where the data from a hard disk to the memory is being transferred. So if that is happening, then in that case we should lock the frame so that this frame accidentally doesn't gets this thing. So for this purpose, for variety of reasons, frame locking is required, and for this for us to be able to implement such a thing, then we can clearly see that what we require some kind of a lock bit associated with each frame. So we have seen that with each frame we require a reference bit which tells whether the page is there in a memory or not there in a memory. Then we say that we have a dirty bit which tells whether page has been modified or not modified, and we have also we find that okay, we also require a locking bit which essentially tells whether the frame is locked or unlocked frame. So let us try to in a next few minutes, let us try to look at a few page replacement algorithms. So any algorithm which one would propose, the first and a foremost requirement would be that the algorithm may want the lowest page fault rate. And so how do we evaluate the algorithm? So what actually we do is we choose a memory reference string, and for this memory reference string we use for testing the algorithm. So in this case, what we are doing, we have a reference string which is given here, where this is essentially, it is indicative that you have a page number 1, then you are accessing a page number 2, then page number 3. Please understand one thing, that when we are talking about a page may have a number of entries, meaning to say a page has a size. So I say that page has a 4 kilobyte of a size. So once you access the page, and inside the page you have a offset. So all the offset inside the page is when you are accessing the page, then your page number is going to be same. Only thing which is going to change is going to be the offset. So once a page is brought into the memory, for some period of a time one would keep executing within that page, and then when you go out of that page, then you make a next reference. So that is what it is indicative of. So here we have shown a string where we are saying that page number 1 is accessed, then 2, then 3, then 4, then 1 is accessed again, and so on. So this is our page string. This is the string, reference string, and we'll try to use this string for various algorithms which we're going to discuss in this lecture. So one of the very simple and popular algorithm is a first in first out algorithm. As the name itself suggests, that as a part of a replacement, the page which was brought in the beginning will actually be replaced. That is why it is known as a FIFO. And then the other thing is that one would need to decide right in the beginning. See, when we are talking about a load on a demand, so the question arises, what is the minimum number of a frame that should be allocated to every process? So for the time being, I am making a statement which you take it from me, that I am saying that the minimum number of a frame which should be allocated to a process depends on instruction set architecture. This aspect I will describe a little later, probably after 2 or 3 slides. I would try to describe why this is the case. So I am saying that let us assume that the frame which is allocated to a process is, we have a 3 frames at a given point of time, because the system has a finite resource, and every process is allocated a some amount of a resource at given point of a time. So let us assume that 3 frames are allocated. So now when the first string is, so this is a indicative, these are the boxes indicative of a frame. So when first reference, that is a 1, is generated, so the first frame gets fetched from the hard disk and it fills, then 2 is referenced, so the first is already brought in and the second frame is brought in. Now the third reference 3 is encountered, so third frame is brought in. Now at this point of a time, if I try to look at that, all the 3 frames are filled. You should also notice that with each reference a page fault is occurring, because in the beginning all these frames would have been empty, these 3 frames would have been empty. When 1 was made, it was swapped in, when 2 made, the 2 was swapped in. So every reference is, every first reference, as sometimes back I had said, that every first reference is going to result into a page fault. So we find that these are the 3 page fault which has occurred. Now 4. Now your program, while you were executing in the area the third frame, probably you made a reference to the 4th frame. Now all the 3 frames are filled. So now we need to take a decision to replace a frame. So as this algorithm says first in first out, so we know that the page number 1 was brought in first, therefore this is the one which will be selected and it will be replaced. So we replace it. So when we replace, so now the 1 gets replaced by 4. Now the next reference is a 1. So now we find that the 2 was referenced last. So the next last, so now 2 gets replaced. So this happens. Now the 3 gets replaced, and you should see here in this gap, in these I am not indicating anything. So essentially this is meaning what, that when after bringing in the 5, the next reference is 1, and that frame is already there in a memory, so we need not bring it in, this is already existing. So there is no page fault occurring, there is no change occurring. Similarly, when next frame is referenced, there is no change occurring. So these 2 references, they are not causing any page fault, because the pages are already present into the memory. And now when we try to see that when the reference to a 3 is made, then 3 is to be brought, and reference to 4 is made, 4 is to be brought. So in this case, in this algorithm, we can now count the number of a page fault which has actually occurred. So we find that 1, 2, 3, 4, 5, 6, 7, 8, 9. Total number of 9 page fault has occurred. And if you see that you have a total length of a string which you are having is a 12. There are 12 references. So out of a 12, we find that 9 references have caused the page fault. So in case of a FIFO, we see that we have a 9 page faults. One thing you should observe here, what is happening, that in this case, if we look at that, see, after the first 3 reference, when the 4th reference was made, so it replaced the frame which was containing the page number 1, and 4 was brought in. So 1 was swapped out, and just after the page was swapped out, and reference to that particular page was made. This is true for all these references. So actually we can very clearly see that in case of a first in first out, such a scenario can occur, that a page which is likely to be referenced at a very next moment of a time, and it could happen that the page could get actually swapped out. So this has actually led to a performance degradation. If somehow we had some kind of a mechanism where it was prevented, then so many page faults would have not occurred. So that is the one thing to note. Then second thing which one needs to note down here is that normally we will feel that if we have a larger number of frames allocated to a process, probably the number of a page fault which are going to be there is smaller. This is a general common sense kind of a thing. We feel that, but let us analyze this statement and see that whether it is true for a first in first out or not. So for doing so, that what I have done, that in my next example I am going to assume that I have a 4 frames instead of a 3 free frames. I am allocating 4 frames and I am trying to run the algorithm with the same string. So in this case we can see that I have a 4 frames and the various page faults are indicated here. So without actually getting into a description of each of the thing, which is a pretty self-explanatory, what we need to do is we need to just count that number of a page fault which has occurred, and in this case we say that 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we find that we have a total 10 number of a page fault. So we can clearly see here that in a previous case where the number of a frame which was available was a 3, only 9 page fault occurred, but when we increase the number of a frames to 4, there are 10 page fault, which is contrary to the normal belief, and this was observed with the FIFO algorithm by a gentleman named Belady, and that's the reason this kind of a thing we call as a Belady anomaly. So we can say that a FIFO usually suffers from a Belady anomaly. We would see that whether other algorithms they suffer from such an anomaly or not. Let me tell you that FIFO is the only algorithm which suffers from a Belady anomaly. None of other algorithms they suffer from it. So this is what a graphical representation of a Belady anomaly. With a single frame, we find that since there is only one frame, so the number of page fault in case of a FIFO which is going to be there, or for a matter of fact in any algorithm, is going to be equal to the number of a string, reference string. And then you see with 2 also it remains more or less in this case same, it doesn't changes, 12 page fault. With 3 we found that it reduced, it came to the 9. With 4 we found it became 10. With 5 it drastically, if you choose run the same string and run it, you would find that with 5 the number will go to 6, and with 6 the number will go to the number will be again 6. We should see that beyond a particular, if we keep increasing the number of frames, we can clearly see that after a certain period of a time this becomes constant, and this is for the reason that as soon as the number of unique references in a given string is equal to the number of frames, what happens that the frame you would get to what we call as a constant frame number. So we saw that so we in a previous example we had seen that the problem was that the pages were getting replaced which were immediately required. So the idea here is that another algorithm is proposed here, and the idea here is that we should try to see that the page which is not required for the longest period of a time, so that is the page which should be chosen and should be replaced. So so this gave rise to an algorithm which we call as an optimal algorithm, and for this algorithm we've chosen a 4 frames and try to see that how this algorithm works. So we know that the first 4 frames they would get filled. Now at this point you see that 1, so 1 is already present, 2 is already present. Now 5 is required to be brought. Now when 5 is required to be brought, I try to see that what are the frames which are existing. So we have a 1, 2, 3, 4. We find out which is the frame which is not required for a longest period of time. So 1 is immediately required, 2 is immediately, 3 is immediately, 4 is later than that. So 4 becomes the victim. So what happens, this frame becomes the victim and it is going to be swapped out. So we bring in 5. Now I execute it up to this point, and after that once again we try to see that which is required. So we find that 5 is required. So okay, 5 we would never replace. We could choose out of 3, probably any one of them. If this is the last then probably any one of the 3 can be replaced and carried out. So in this case one can very clearly see that we have 6 page faults which are occurring in this algorithm, whereas in case of a FIFO there was a 10 page fault. But the issue here is, or the problem here is that for a operating system to be able to implement this algorithm, operating system would need to know the future references, and which is not always going to be possible, or which is not predictable precisely. And that's the reason that this optimal page algorithm is usually not implemented, and it is essentially it becomes a benchmark. It is used as a standard where all other proposed algorithms performances are compared against the optimal algorithm. So the other proposed algorithm, their performance is always going to be less than or equal to the performance offered by optimal algorithm. So we have tried to see that if the algorithm is in a previous case we tried to see that a frame which is least likely to be used in future, we were doing it. Just a reverse thinking here is that if suppose we choose a frame which is least recently used, meaning to say which has been used too far away in the past, so there is every likelihood that this frame may not be required to be used. So this is what least recently used algorithm is. So we can see that again the implementation is shown with the help of a 4 frames. So first 4 frames are fault, then 1, 2, since they are there, no, then now 5th is to be brought. So in this case what we try to do is we try to find out a frame which was which has not been referenced for the longest period of a time. So we find that 1 was referenced here, 2 was referenced just before 5 was, and 4 was referenced, but 3 was referenced much later. So from this what happened, that the 3 would get replaced. So that is how that 5 comes here. In same manner we can see that this is what it is going to be. So if we try to count the number of a page fault in this case, we find that now the number of a page fault is 8, though it is greater than optimal, but it is less than the FIFO. What we'll try to do is, this is one of the most widely used replacement algorithm with some changes. So we'll try to devote a bit of a time discussing about the implementation of the various possible implementation. So LRU implementation, one of the implementation is we call as a counter implementation. So we say that every page entry has a counter, and every time page is referenced through this entry, what is done, the clock is copied into the counter. So we have a system clock and this clock we can say is a logical clock. Logical clock in the sense that it could be some simple counter which is with every clock tick it is increasing. It is not a hourly clock where one is recording the hour, minute and second. So hour, minute and second and a date. So it is some kind of a clock, logical clock, where the value keeps getting incremented, and whenever a page is referenced, the logical clock value is copied into the counter. Now in this way that we can very clearly see that all the reference frames would have a counter value associated with them, and then a selection becomes very easy, that we need to choose the frame with the counter value which is a smallest counter value. So so that is how the decision can be actually made. But then in this case we can very clearly see that the question arises is that what should be the size of a counter. So if we keep a very large counter value, let's say that for a single byte if I keep a 32-bit counter, then it is a very large amount of overhead for a 4 gigabyte of a memory or for a 1 gigabyte of a memory. I am saying that for every byte I am going to have a 4 byte of a counter, then for a 1 gigabyte of actual memory which is getting accessed, what I would need to maintain is a 4 gigabyte of a count memory for storing the counter for those references. So there is a very large amount of overhead. So the size, here is a trade-off in terms of the size of a reference bit which one would maintain for this. So the another implementation is in terms of what we call as a stack implementation. So what we do that whenever keep a stack of a page numbers in a kind of a doubly linked list form, and what is done that whenever a page is referenced, so what we do, we move that reference page to the top of the stack. So in this case, as we can very clearly see that in this top of a stack would have a frame which is a most recently referenced, and a bottom of the stack would have a frame which is a least recently accessed, and then so that essentially means that we would not require to search the frames. What we can do is we can sort of very easily get the replacement page. It is a kind of a thing where what we are trying to do is we are trying to create a queue. And as earlier also mentioned that this LRU algorithm does not lead to a Belady's anomaly. We would just try to see, as we said, that if we are talking about a counter implementation, then it requires a large number of bits. So what are those approximations? So there are a few proposed algorithms with a certain approximation. So what is done here is that only one counter bit is maintained, or one reference bit is maintained with the LRU. So initially while each page is associated, initially the reference bit is marked as a 0, meaning to say the page has not been referenced, and when the page is referenced the bit is set to 1. So if we take a snapshot of frame references, frames which are there in the memory and their reference bit, so we can broadly classify that there are certain set of frames which has been referenced, and there are certain set of frames which have not been referenced. So this essentially divides the frame into a two category, reference frame and not reference frame, but it doesn't gives me any order in which the frames have been referenced. So that aspect we should understand. So what happened that our replacement policy could be that the frame which has not been referenced, those are the ones which which should be chosen, or which should be chosen for a replacement. But then the replacement actually is required that when all the frames have been referenced and they have been filled and brought in, and there is no free space. So the assumption in this case, there can be a situation where we would find that we don't have any free frames. So the algorithm this LRU algorithm at time is when we start looking at in terms of implementation, what happens that it's a kind of frames. One of the approaches that the frames are arranged in a kind of a circular list, and we maintain a pointer pointing at a next victim which is required to be replaced. So it looks like something like a clock, that where you have at a periphery you have a number and you have a clock hand which points at a specific number. So that's the reason that there is the LRU implementation, there is a clock implementation. Maybe in another few slides we will try to show you the diagram which will make things a little bit more clear, that how the clock algorithm works. And there is a change, there is a algorithm which is proposed for a replacement, and we call it as a second chance algorithm. As we say that what happened, that we try to replace a frame, we are having a pointer which points at a next victim, and now what happened, that the next victim happens to be, let's say that the next victim, the reference bit is 1, that means that it has been referenced, but it is a victim. So it may result into a scenario where you swap out this page and immediately this page is going to be required. It is possible that this frame was immediately brought, and it just happened that since because of a clock implementation, it's something which becomes immediately it is going to be replaced. So it is said that since the page has been referenced, the argument is that since the page has been referenced, it can be given a chance. We don't replace it immediately because there is every likelihood that it will be referenced in the next reference. So with that, what we do, we try to give that particular frame a second chance. So there is this gave rise to what we call as a second chance algorithm. And in this case, what actually happens, that the reference bit which was 1, and the pointer, the clock pointer which was pointing to this frame for the purpose of a replacement, a suitable frame. What is done here is that we change the reference bit to 0 and advance the clock pointer to point to the next frame. In this way, we exhaust all the frames. So it is possible that if suppose all the frames were marked with a 1, then by giving a second chance, what would happen, that once again we will return to the first frame and replace the same frame. But let us look at a diagram which will show that how actually things can actually happen. So in this case, I am saying that we have a snapshot here. We are saying that we have a circular queue of pages which are maintained like this, and I have a next victim pointer which is pointing, and for these pages, as I said, that we will maintain a reference bit. So we find that for this victim page, the reference bit is 1, and what we are saying that we are going to implement a second chance. So idea here is that this particular frame which has been referenced, we avoid replacing, because of the logic that this page has been referenced and it is likely to be referenced in near future. So what we do, we make this bit 0 and advance this pointer to the next one. Fine. So, this bit becomes 0 here. Now, you have advanced your pointer to here. What happens? This page is also 1. So, we need to give a second chance. So, again we make this 0 and advance our pointer to this place. So, you can see that this has been made 0 and the pointer has been advanced to this. Now, when it is advanced to this, incidentally here what happened, that we find a frame which is for which the reference bit is 0. That essentially means that the page has not been referenced. So, what happened, that this is an ideal thing we will replace. So, this is how the second chance LRU functions. So, in case of a second chance LRU, we can very clearly see that what we are doing, we are making our decision based on whether the frame has been referenced or not referenced, and if the frame has been referenced and it is a victim frame, then we give it a second chance, and this process we would repeat for every single frame to choose a suitable victim frame which will be used for purpose of a replacement. But then in addition to this, an enhancement was proposed to a second chance algorithm, where what is done, that there is a additional bit, one extra bit is made, because one should look at that. Let us say that this particular frame, when we select for the purpose of a replacement, there is a likelihood that this particular frame is dirty frame, and it is going to be it would require a swap out before swapping in. So for that reason, that what is proposed in case of a second chance algorithm is that in addition to a reference bit, what we do is we also use a bit which is a modify bit. So this is a what? So instead of a 1 bit, we would have a 2 bit. One is a reference and another is a modify bit. So these 4 combinations we can very clearly see that they would arise. That is a 0 0. So 0 0 could actually corresponds to not referenced, not modified. If modified bit is 0, that essentially means that the frame is not modified. If modified bit is 1, that essentially means it has been modified. Then I have a 0 1, not recently used but modified, recently used but not modified, and recently used and not modified. So we have a 4 different combinations, and the best combination would be that something which is not referenced and not modified, that would be the best combination. So we can have, and this could be the least preferred combination. So the second chance algorithm, enhanced clock policy or enhanced second chance algorithm could be used for giving us a better performance. We just here is a comparison for various algorithms. So we can very clearly see that FIFO performs worst performance is achieved by FIFO, then we have a clock, then we have a LRU, then we have a optimal. There are so in previous cases what was happening is that we were looking at a trying to find out a frame which is least recently used frame, or which is which was used most recently used frame, or some such kind of things we were trying to look at, and based on our algorithm. Another algorithm which is there is in terms of a frequency of the uses. So these algorithms are categorized in the group we call as a counting algorithms. So in case of so what we do, that we try to maintain a frequency of a use of a frames. So here one of the proposed algorithm is known as a LFU, that is a least frequently used algorithm. So So what happens that the logic is that you try to find out a frame with the smallest count value, that essentially meaning to say that the frame has been brought into a memory and it has not been referenced quite too often, therefore this is a most suitable candidate for the purpose of a replacement. But if such an algorithm is implemented, it would suffer from a drawback that there is every likelihood that a particular page has been brought into the memory more recently, and therefore its reference count is very small, whereas there is a page which was brought into the memory long time back, and when it was brought it was accessed a lot, and after that it has not been accessed in the last 1000 references. So there would be a drawback. So these are the drawbacks which would occur. Either we use a least frequently used or a most frequently used algorithm. Both of them would suffer from such drawbacks which I just mentioned. So let us return back. There was I think that a little while ago I said that what is the minimum number of a frame that should be allocated to a process. So I made a statement. I said that the minimum number of frames which is used by which should be allocated to a process depends on a instruction set architecture. So here what I am trying to indicate here is that I have, let us say, a move instruction which moves the content from a source location to the destination location. So the instruction is a move source comma destination, and let us say that the total size of an instruction is 4 byte. So if the instruction size is 4 byte, then we know that and the memory is organized in a byte, memory is byte organized, then we know that it is possible that our instruction will get aligned to a page boundary. Part of an instruction would reside in one page and the next part of instruction will. So out of 4 byte, it is possible that 1 byte is in a first page and 3 bytes are in a second page, and it can be of any combination, 2 byte in a first page and 2 byte in second, or 3 byte in first page and 1 byte in a third, and so on. So there is a possibility. So for storing the instruction itself, one would require 2 pages, and let us say that a source, the data which is being fetched is a multi-byte data. So in that case also the source data could actually reside on 2 different pages, and the destination also could be 2 different pages. So in this case we see that we have 2 pages required for an instruction, 2 pages for a source, and 2 pages for a destination. So total number of 6 pages. So this is how the minimum number of frames are decided. Then we need to also talk about allocation schemes. We have seen that how the replacement is carried out, but we need to also see that there is a minimum number of frame required, but if we need to allocate more than the minimum number, then what should be the scheme? So there are two major allocation scheme. One we call as a fixed allocation scheme, and other we call as a priority allocation scheme. We will see them, that what those are and how they work. So in a fixed allocation scheme, one of the thing could be that every process could be treated equally, and every process could be given a equal number of frames. So if we say that we have 100 frames and there are 5 processes, then we can say that each process could be given 20 pages. But then there is a possibility that there is a particular process, one of the process here only requires 1 page, whereas there is another process which might require a 30 page or a 40 page, which is because that particular process is a large process. So in case of a equal allocation, we can very clearly see that the one process will get allocated the pages which it will never use. So it will be a unutilization, whereas another process would suffer because it is not allocated enough amount of pages. So because of this reason, the next allocation scheme which was proposed was known as a proportional allocation. The idea here is that allocate proportional to the size of a process. So here we say that let's assume that SI is the size of a process PI. Then what we do, we compute capital S, which is equal to the summation of all the sizes, all the process sizes, and then we have M, that is the total number of frames, and then we calculate the allocation in a proportional manner, which is a SI divided by total size of processes, all the processes, and multiplied by M. So if we take an example, here we take two examples. We say M is 64 and a process S1 is 10 and process S2 is 127. So my allocation for the first process would be 10 upon 137 into 64, that is a total number, so 5 frames, and A2 would require 59 frames. So we can very clearly see that if we allocate a proportional, then the larger process would get a larger share of the frames, and a smaller process would get a smaller share of frames. So we just saw that we have a proportional allocation which was based on the size, and instead of doing a proportional allocation, what one can do is one can proportional allocation based on the size, what one can do is one can do it on some kind of a priority. So you try to find out a process which has a higher priority, maybe a system process which requires a larger amount of a share. So based on the priority, you allocate more amount of a memory. So that is another approach which one can resort to. So these are the allocation scheme. Now let us analyze that a situation that okay, when a process I generates when a page fault occurs. So what happened that the victim which we are selecting, we would need to select one of the frames as a victim and replace it. So in case of a priority, what happened that we would need to select the frame of a process with a lower priority number. Our allocation, see, the allocation was based on a priority. Now let us say in case of a page fault when it is occurring, so again the replacement is going to be based on a priority. So in this scheme, what would happen that the replacement, the processes with a lower priority, they would be selected as a victim for the replacement. Their frames would be taken away and they will be replaced. Which has an implication, as we have seen that any priority scheme leads to a starvation. In this case as well, it could lead to a starvation. So we just see that a previous scheme, in case of a previous scheme, what was happening is that because we said that a replacement is going to be based on a priority, and a lower priority process would become a victim and its frames are going to be taken. So in this case, we can see that it led to a scenario where when a page fault is occurring, one is trying to replace a frame belonging to some set of other process. So the strategy here, there are two kind of a strategy for a replacement. One we call as a global replacement, and another we call as a local replacement. So, in case of a global replacement, that when the frame is selected, a victim frame will be selected globally, that is, it could belong to any of the executing process, and that particular frame would get replaced. So, this essentially one can see that in this scenario what is going to happen, that individual processes would have a no control on their page fault. Because well, you just see that the page replacement algorithm would see that okay, they have bought you have got a page into the memory, but because of a global replacement policy, that particular page the page which was very recently brought into the memory, because of a global replacement policy, this particular page gets replaced and it gets swapped out. So, there is a issue with that is what we say, that a process cannot control its own page fault rate. And another approach is what we call as a local replacement, where each process selects the victim page from its own set of allocated frame. So, in that case what happened, that within the since the replacement is within local, it is confined to the process which is executing, it does not impact the other processes. And usually there is a very important concept when we talk about a load on a demand. This concept is known as a concept of a thrashing. And thrashing, we say that if process does not have enough pages, then in that case what happens, that while the process is executing, it is doing this process is page faulting. The page fault rate for the process is very high. So what is happening, that when a process is executing, more of a page fault handling is happening than executing the process. And whenever such a scenario occurs, we describe such a scenario as a thrashing. And this leads to, so if large number of a page fault is happening, then the processor is required to execute the page fault handler quite too often. So this actually leads to a low CPU utilization, because every now and then the process is going to be suspended. So it leads to a lower CPU utilization, and it can actually happen that when the CPU utilization reduces, the operating system would feel that it needs to improve the CPU utilization. Therefore, what it might try to do is, it might try to bring in the new additional processes to increase the degree of multi-programming in the system. And with the additional set of processes coming into the memory will further get reduced, resulting into a more amount of a thrashing. So we find that thrashing is a very serious issue. One needs to thrashing can be defined as a process. Process is busy swapping pages in and out, and it is not doing useful work, and we find thrashing is quite predominant in a global page replacement policy. So this is an example here. So what happened, that CPU utilization, so when one increases the degree of multi-programming, that is a more and more number of program in a memory, so the CPU utilization keeps going up. So we find here that in this diagram, what we are trying to show is that if we go beyond a particular point, then increasing the multi-programming results into a degradation of a performance. So at this point you can see that when you try to add one more process, bring in one more process or a few more processes, what happens, that the performance starts degrading, it goes completely flat, and this primarily occurs because of a thrashing and because of a resources not becoming available. So, each process they start suffering. So, there are questions which one needs to answer is that we talk about a load on demand. So, the thing is we are trying to bring in a very small amount of code which is going to be executed at a given point of a time, or a data which is required into the memory. So, the question is that why such a thing works. The answer lies in what we call as it is observed. There is a locality model, and it is observed that most of the program they follow what we call as a principle of locality of a reference, and processes migrate from one locality to another localities. These are the things, the locality model which is there. Because of a locality model, this works, the paging works. So, the principle of a locality of a reference is there, and there we say that if a particular frame has been referenced, then it is pretty much likely that the frame would get referenced once again. And another thing is said that if a location is accessed, there is every likelihood that a neighboring location will also get accessed, and this is true for most of the way programs are written. This is true for most of the cases. So, so we know that why the paging works, and the question is that why does thrashing occur. The thrashing primarily occurs when the size of locality, the summation of size of locality is greater than the total memory size, then the thrashing would occur. So, how do we handle the thrashing? So, for handling the thrashing, there is a algorithm which is proposed, which they call as a working set model. So, what is done here is that we define a delta which we say is a working set window, and this is a fixed number of frame references. So, we can say that a working set window is 1,000 references or 1,000 instructions. And then we define something known as a working set of a process, that is a WSSI. So, this is a working set of a process PI. So, what we try to do is WSSI is a total number of pages referenced in most recent delta the working set window. This will be very clear to you once I start explaining it with a example. So, we say that if delta is too small, this will not encompass a complete locality. You may have, we should have a delta large enough to in general encompass a locality. If delta is too large, then same delta can encompass several locality, and if delta is infinite, then the entire program would become a single, it will come into a single locality. We define D as a parameter here. We say D is equal to summation of WSSI, that is a total demand of a frames, where WSSI is a working set for a process I, and D is a total demand. If we add all the working set of all the processes, then that is a total demand. So, the strategy here is that if D is greater than M, that is a total number of available frame, then thrashing is going to occur. So, the policy here would be that if D is greater than M, then suspend one of the process. This is how we would handle it. This can be one of the way of handling the thrashing. Let us see an example. So, in this example, we are choosing working set of 10 references, that is a 10 references. So, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So, in 10 we create in this window we create a WSSI S working set at a instance T1. So, in this we try to find out what is the unique number of frames which are required there. So, we find that we have 1, 2, 5, 6, 7. Out of 10 references, there are 7 references. So, here the working set model has a value which is a 1, 2, 5, 6, 7. So, it lists 5 frames. As you keep executing, keep moving forward, at another point of a time when you see, you find your working set window has a only two values. So, the working set gives me a clear cut idea that what we can do, we can calculate the working set for each processes, and based on the available and requirement, what we can do, we can take a decision in terms of suspending or aborting a process and handling the thrashing. The another much better approach would be that what we do is we try to, instead of creating a working set window, the another simpler approach could be that what we could do is we could set a page fault rate and 2 upper bound and a lower bound. If the page fault grows beyond the upper bound, then what we do, we increase the number of frames. If page fault goes below the lower bound, then what we do, that we decrease the number of frames allocated to the process. So, this is how the thrashing can be actually avoided. And there are several other considerations. It is not that just by looking at frequency one can do it. There are other considerations which are taken into account. There is a concept what we call as a page buffering. So, in this case, what is done, that we maintain a pool of free frames to quickly restart a faulting process. Because what happened, that we know that if suppose a page fault has occurred and we are trying to look at a replacement, and we find out a frame which is a dirty frame, then the search goes on. So, what we can do, we can actually maintain what we call as a free frames, and which can be utilized immediately as soon as a page fault occurs. And there is another thing that we call as a pre-paging, and we find that what actually happens, that whenever new process, when a process completely gets swapped out and it is brought into the memory, then initially there are going to be a large number of page faults which occur. So for that reason, what one can do is one can bring in a complete working set of a swapped out page. That is, all the processes, all the pages which were swapped out for a given process, they can be actually brought into at a one shot. So, the initial multiple page faults which occur, they could actually be avoided. There is another consideration. The other consideration is in terms of a TLB reach. TLB, we have seen that TLB is known as a translation look-aside buffer, and we find that the size of a TLB specifies that most recently translated addresses it keeps. So, TLB reach is defined as a TLB size multiplied by the page size. And ideally, the working set of each process is stored in the TLB. The way this thing. If the working set of a process is not stored in the TLB, then there is going to be a good amount of a page fault that would keep occurring. the there is another important thing which can be looked into which is looked into for avoiding the thrashing. So the scheme here is that we know that here we are trying to indicate an example. We say that we have defined an array which is a 1024 cross 1024, that is a array of 1024 into 1024 elements, and we can say that each row is now how the array is actually stored in the memory. It depends on that. So we have a notion of what we call as a row measure and a column measure. So it is possible that each row, let's assume that each row is stored in one page. So we have a 1024 rows, and therefore these 1024 rows are going to be stored in a 1024 pages. So now if suppose we write a program where we are trying to access the first element of a first row and then first element of a second row and so on, then we know that there is going to be a so many page faults which are going to occur. So it is important for a programmer to know about that how the information inside the machine is getting organized, let's say in terms of a data structure. So for an array, if it is organized in a row measure manner, then it is better to access the information completely from a row rather than accessing it as a column. So these are the few considerations which can this is purely a thing which programmers should be aware of to reduce the issue of a thrashing. Thank you very much.